Hello. Today we will discuss LUP decomposition of matrices. This decomposition will break a matrix into product of three matrices. This will be a square matrix which is lower triangular, which means all the entries above the triangle, above the diagonal will be 0. This will be a matrix which will have all the entries below the diagonal to be 0, and P will be a permutation matrix. So let's just first of all make sure we know what a permutation matrix is. P is a square matrix of size x by x, is a permutation matrix if there is exactly 1 1 in each row and each column, and all other entries are 0. So any given row and column has only 1 1. So identity matrix is a permutation matrix. Similarly, in 2 by 2 this is a permutation matrix. The application of a permutation matrix on another matrix from left. So suppose this is 2 by 2 matrix, and let's say this is 2 by k matrix. Then the application of this matrix on this is effectively permuting the rows of this matrix. Similarly, if I am applying a permutation matrix from the right hand side, if I am multiplying from right, we are permuting the columns of this matrix. And what exactly is happening in this case is that we have over here row A1 and here row A2. When I multiply, I am going to get the entries of A2 first and the entries of, because when I multiply here I will get the entries of A1. So this is exchanging the rows here. In 2 by 2 you do not have too many other cases, identity or this. Similarly, if it is a larger matrix, it will be some general permutation. Now in general, a permutation can also be expressed in form of cycles. So for example, if I have 1 2 3 4 5, this means that 1 goes to 2, 2 goes to 3, 3 goes to 1, 4 goes to 5, 5 goes to 4. So the corresponding matrix, in the sense that the same effect it causes on the object to its right, can be achieved by noticing that this has to be a 5 by 5 matrix, and the first row, if I am multiplying from left, so I am permuting rows. So the first row must go to the second position. To do that, what we have to do is put 1 in the second place, 0 0 0 0. The second row must go to third place, so this will be 0 1 0 0 0, and the third row should go to the first position, so it will be 0 0 1 0 0. Notice that these three rows are going to effectively achieve this permutation. The fourth should go to the fifth place and the fifth to the fourth. So to fourth, fifth should go. So we have so it is easy to construct such a permutation from this, and similarly one can go backwards. Further, if I have to multiply two permutation matrices, we can actually directly perform that through this representation. and such a computation can be done in the time of the individual dimensions. So, if this is k by k, the multiplication of two k by k matrices is certainly worse than k square, but this we can do in order k time. Now, this information will be coming in handy later on. There is one result that I would like to describe here before we proceed to discuss LUP decomposition, and that is the following. Suppose we have a matrix M of size M cross N, and we have N of size M cross N, and we consider the product N dot N. Suppose and further assume that M is less than equal to N for convenience. Assume that the matrix M is full rank. What does that mean? It means that when M is less than equal to N, there is a submatrix of size M cross M which is non-singular, and that information is equivalent to the fact that in this M cross N matrix the rows are linearly independent. Equivalently, in terms of columns, there exist M columns which are linearly independent, which N we may not know. Now, suppose we have a matrix N which is non-singular, hence this is also such that the rank is M. This also has rank equal to N. In that case, the product, let us call this M prime, then the claim is that the rank of M prime is also N. To prove this, observe that the rows of M prime are combinations of the rows of M. So, the rows of M prime are linear combinations of rows of M. Why? Because if you take a look at, you are multiplying, say you take the first row of N and you multiply. So, those coefficients are multiplied to various rows of M and you combine them, that makes the first row of M prime, so on. So, each of the row vector of M prime is combination of rows of M. Now, suppose M prime has rank strictly less than k, less than M. Then for any N prime, M prime must have rank strictly less than M. The reason is, once again, if the rows of this are linearly dependent, then these are further combination of the same rows, they cannot be linearly independent. Hence, this must also have a rank strictly less than M. Now, if we take N prime to be n inverse. Notice that our n is a full rank matrix, hence its inverse exists. Full rank for a square matrix is equivalent to non-singular. So, rank of n inverse m prime is rank of n inverse n m is equal to rank of m, which is less than m. That is absurd. Hence, we conclude that if this is full rank, note that the rank cannot be more than the smaller of the two dimensions, and smaller is m. So, this is m, this is m, then the rank of m prime must also be m. Okay, so this is a small result that we are going to need. Now, let us talk about LUP decomposition. What we will show is going to be stated in a theorem. Let me state that. So, let T be an m cross n matrix of full rank and m is less than equal to n. Then there exists a lower triangular matrix, square matrix, which is actually m cross n L, and an upper triangular matrix U that will be of size m cross n and a permutation matrix P of size n cross n, such that all diagonal elements of L and U are non-zero, and our original matrix is the product of L, U and P. Now, one word about this matrix. This matrix is not a square matrix. So, what we mean by upper triangle is that this is the diagonal, these are the elements A, I. So, everything below this is 0. This is the way U should look like. Of course, L is this would be 0. Okay. So, we will prove this theorem by actually giving an algorithm to construct the three matrices. Now, the base case will be when m is 1. So, let us say proof by construction. We will use recursion in construction, and our base case is when m is equal to 1. So, we have our T which looks like a 1 by n matrix, 1 by n matrix. Now, all entries of this cannot be 0 because its rank is 1. Okay. And there has to be some place, some jth location, say jth location, where we have x and x is not 0. So, one can rewrite this in the fashion 1 times x here in case j is 1, in that case we do not have to worry too much, but say this is 0, then we will have the value whatever this value is, say 0 will be 0 here, and a permutation matrix P which swaps the first position with the jth position. Okay. We know how to write such a permutation matrix and leaves everybody else in its own position. This is a lower diagonal matrix, lower triangular matrix. The reason is that it has only one entry and that falls on the diagonal. As we require all the diagonal entries must be non-zero, and indeed it is non-zero. On the second matrix, the only diagonal entry is 1 1, the position 1 1. That by construction is non-zero. There is no entry below this diagonal, hence we do not have to worry about this, and this will qualify as an upper triangular matrix. This is a permutation matrix. Hence, we satisfy the requirement for the base case. Now that we are done with the base case, let us take an arbitrary matrix of size m cross n. Once again, remember that m is less than or equal to n. And we split this matrix anywhere. So, this is some m1 and this is m2. Let us call this submatrix T1, this as T2. Now, notice that since m is less than or equal to n, the full rank meant all the row vectors are linearly independent. As a result, the row vectors in T1 are linearly independent and so are in T2. Hence, T1 and T2 themselves are also full rank, and we are in a position to perform LUP decomposition on them. So, let us suppose in step 1 we perform the LUP decomposition by recursive call of this algorithm, and we get the lower and upper triangular matrices. So, I am going to, in this case, I am going to call this as U1 and the rest of the matrix, submatrix as A. And then we have a P matrix. Note that this is M1 by M1, this is M1 by N. Maybe I will split that. This is M1 and this is N minus M1. This is of course an N cross N permutation matrix. This is M1. Now that we have this decomposition, we can rewrite T as T1 0 0 identity. This is M1 and this is M2. By the same token, this is M1 and this is M2. This is U1, this is A. We have T2 here and we have a P there. Now note that the upper part is unaffected, because when you multiply, the 0 does not contribute anything. 0 multiplies to T2 does not change anything, and we really get T1 U1 T1A, and then of course P from that. On the other hand, this portion is also unaffected. I times T2 is T2, but after that this is going to be affected because of P. To deny that change, we will have to multiply by inverse of P. Note that every permutation matrix is full rank, is non-singular, its inverse exists. Yeah. This is L1. My mistake. This is L1. So now this is a starting decomposition of T, but we have yet to go further. The reason is, this indeed is a lower triangular matrix, because this is lower triangular, this is identity matrix which is lower and upper triangular, and this is 0, but this is not. So now we have to further modify. So in the next step, maybe we will just relabel this in the following fashion. We will call this Ti00. Here let's call U1, and this portion, this is A, this is B, let's call this F. I think I'll call this F. So this is still M1, and of course we have M1 and M2 here, and of course multiplied to P. Now in the next step, we will attempt to make this part 0. Now to do that, we have to ensure that the contribution, which is F when we go in this part, is still maintained. And for that, what we will do is, we will set this to 0, and this will be such that when multiplied here gives me F. So that can be done by replacing this by FU1 inverse, FU1 inverse, this will stay there, and we have a this is still U1, this is A, this we will set to 0, and we will have a P here. Let us look at the impact of this change. This, when multiplied to this column, this part of the matrix, we are going to get F back. That contribution will be intact. But when we multiply this here, this was B earlier, so B will be still there. We will also get FU inverse A, which we must eliminate. So we got to replace this by B minus F U1 inverse A, and that will make things equal to the original product. Now let us call this matrix C. This is still equal to T. Now we knew from our theorem and from induction hypothesis that all the entries of the diagonal entries of L1 are non-zero, all the diagonal entries of U1 are non-zero. So, first thing is, since diagonal entries of U1 are non-zero and this is a upper triangular matrix, from our last lecture we know that such a matrix has inverse, and we can compute that in the same time as matrix multiplication of size m1 by m1, and hence this step is valid, computation of U1 inverse. Secondly, since all these entries are non-zero, the diagonal entries are non-zero, these are also non-zero, hence this matrix over here with FU1 inverse, this is a lower triangular matrix. Once again, in principle its inverse exists. Now, suppose this we call some L prime, then L prime inverse T is this matrix times P. At the start I had pointed out that if this is a full rank matrix, this is a full rank matrix, then this product is also a full rank matrix. Hence, this product is a full rank matrix. But this is a permutation matrix, it just permutes the columns, does not change the rank. Hence, this matrix must be a full rank matrix. Once again, because this is full rank, this part should be all linearly independent rows. So, this submatrix also is a full rank matrix, which is actually M2. Notice that this is of size M1 and this is size M2. So, this is a full rank matrix. But these entries are all 0. Hence, this submatrix must also be full rank. Once again, we have a full rank matrix, so we can recursively apply this LUP decomposition on C. So, in our step 3, we compute C equal to U2 we have lower triangular matrix. So, L2, U2 and some matrix D followed by P2 prime. I choose to write P2 prime. So, let us try to first verify our dimensions and all. These are, this was M2 by N minus M1, N minus M1 size. This was M1. So, both of the dimensions of L2 are M2. This is M2 by N minus M1 size. This is M2 and this, okay, we will split it here. This is M2. This is N minus M1 minus M2, but M1 plus M2 is M. So, this is N minus M. This should be a square matrix of size N minus M1. So, this is N minus M1 cross N minus M1. Because this is going to be multiplied to this matrix. Now, again keep in mind that the diagonal entries are non-zero here, diagonal entries are non-zero here. So, let us try to rewrite our P recognizing this factorization, So, we will put L1 here, FU1 here, we will put L2 here, this will be 0. You have U1 and a 0 here, A. Let us see if we put T here, we will put a P2 and a P1, where P2 will be P2 prime here, a unit matrix over here of size M1 by M1. So, this is M1, this is N minus M1, this is also N minus M1. Now, is this correct? So, let us first look at this is an expression, this was P1. Okay, I would like to make this P1 because we have a P2 sitting here. The effect of multiplying the upper part with L1 will be same, except that we have now P2 sitting in between. To deny that effect, we will put a P2 inverse here. Now, if you just look at the multiplication of this part, it is like L1 multiplied to U1, L1 multiplied to A P2 inverse. The reason we do not have to multiply anything here, P2 prime inverse, P2 prime, the smaller matrix is P2 prime inverse. The reason is that in P2, this portion is identity, which does not affect this fellow, and P2 prime is going to be multiplied to A. So, that is cancelled. The lower part, when we go about multiplying this way, the contribution from identity was that we were getting directly C followed by multiplication of P1. This time we are going to multiply L2, this is going to be 0, but L2, okay, this has to be UD, U2D, this full vector sitting here. Now, L2 is being multiplied to this part followed by P2, but since this corner is identity, we are going to be effectively multiplying identity to this and P2 prime to this. So, we will exactly get C and followed by P1. So, this is now the new form of T. At this stage, what we have is a clear lower triangular matrix, because here this is lower triangular, this is lower triangular. All entries are non-zero at the diagonal here, all entries here are non-zero at the diagonal. So, the entire diagonal is non-zero. So, this is what we want as a lower triangular matrix in this part. Here it is an upper triangular matrix, exactly the same is true, all the diagonal entries are non-zero, only thing is the zeros are on this side. So, this is 0, here it is 0, here it is 0. So, this matrix is actually a square upper triangular matrix, and this is also upper triangular matrix. Hence, we have completed the transformation of the matrix T into product of these three, well, these are 4 matrices. Now, we can replace this by a product matrix P, which is the product of 2 permutation matrices, is also a permutation matrix. So, we get a complete decomposition into lower triangular, upper triangular and a permutation matrix. Now, at this stage we will like to determine the cost. So, now let us take each step and count the cost of each computation. In the first step, we have taken the upper half matrix. We are going to pay the price of transforming an M1 by N size matrix into this product. Now, to do all this, first thing I am going to assume is that T of M denotes the transformation, the cost of transforming an M by N matrix into LUP matrices. I will not indicate N here because that is a background parameter, will not show up too often. The cost of this computation therefore will be Tm1. Now, let us say M bar denotes the nearest power of 2 greater than or equal to M, and we always break as close to middle as possible. That is, if this is even, then we will just split in the middle. If it is odd, then one will be slightly off. In that case, both M1 and M2 will be less than equal to M bar by 2, M2 will be less than equal to M bar by 2. This will always be the case. So, we will simplify our life and think of M as M bar. This will be less than equal to, first factor is T M bar by 2, that is coming from this step. In the next step, well, in the very same step, what we have done is we have multiplied P1 inverse to T2. Now, multiplication by a permutation matrix, so remember P1 inverse is also permutation matrix, is like permuting the columns. But permuting the columns, we do not have to do a regular matrix multiplication, but we can simply read the permutation and write down the columns. Therefore, this can be done in order of the size of this matrix itself, and that would be N into M bar by 2. So, I will add a cost some C1 times N into M bar by 2. That would be the cost of this step. Then we have computed inverse of U1, multiplied it to F, then multiplied it to A, and then we have subtracted this from B. So, there are these steps. Now, computation of U1 inverse, we have already shown in the last lecture that the inverse cost is of the order of the same as that of multiplication, and this is true for triangular matrices. So, this I will denote by writing down M bar by 2. M is the cost of multiplying two matrices of this size. That is the cost of inverse. Now, we multiply this to another matrix of same size. So, which is again the same thing. So, we can say put 2 here, and then we are multiplying this to a larger matrix in general. A is M by 2 by N minus M by 2. Now, notice that if you have to multiply X by X matrix to X by Y matrix, Y is say larger than X, then we can think of this as split into matrices of size X by X, X by X and all that. So, that cost can be M X into Y over X. because that many submatrices are sitting, so that many multiplications are there. So we can add this. So let me just clean up, and we have the cost of n minus m bar by 2 by m bar by 2 of m bar by 2. That accounts for this multiplication, and then subtraction is 1 unit work for each entry. So that costs us m bar by 2 into n minus m bar by 2. That many entries are there in this matrix. So next step is the application of P2 prime inverse 2a. As we have seen earlier, we can do this by simply permuting the columns. Will cost us as much as the size of this matrix, that would be m bar by 2 into n minus m bar over 2. The only thing which looks threatening is the multiplication of these two matrices. Both of them are n cross n, and if I try to write mn, that would be very costly. But recall that at the start we said these matrices need not be kept as matrices. We can store them in the form of product of cycles, and the multiplication of these two permutations can be done in order n rather than order mn. So this whole thing will cost us some C2 times n. That is the product of the 2 n cross n matrix. I forgot, there is one more operation we have performed. This is where we have applied the LUP decomposition on C. C is of size m2 by n minus m1. Since we have kept n as a suppressed parameter, we will not worry, we will think of this as n, which does not really hurt, and this will be m by 2. So this decomposition also costs us T m by 2. Now that accounts for all the computations we have performed. Now let us try to clean this up. We have 2 of T m bar by 2 because of these two, and we have, if you account for this and this together, this is going to be n by m bar by 2. So 2 of that m. So we can actually put some constant here other than this. We will put some C m bar by 2. That accounts for this entry and this entry together. Notice that this multiplication is at least square of this entry. So this entry is more than m bar times n into some constant. Hence, this entry is subsumed by this. This entry is subsumed by this. This is subsumed by this, and this is also subsumed by this. We don't have to put any more entry. For a suitable choice of constant, this can be taken as an upper bound to Tm bar. Now all we have to do is simplify this and solve for the value of Tm prime. So if I expand this, I am going to get this as C n m bar by 2 by m bar plus 2 of the lower size, lower. So there will be 2 here, this will be replaced by m bar by 2 square, this will be m bar by 2, which will be 2 square here. One more term maybe. This will be 2 of this. So we have a 2 cube here, m bar by 2 cube over m bar by 2. So that makes it 4. This is the expansion of this recurrence relation. Now, recall that m of m is about some m to the power 2 plus epsilon. So we can say that m by 2 is approximately m 2 plus epsilon by 2 power 2 plus epsilon, or we can say that there exists an epsilon from which we can bind this. So if I take 2 to the power 2 here, we can say this is bounded by m over 2 power epsilon. So we will use this inequality and rewrite this as C n by m bar that makes it m of m bar m of m bar by 2 is 2 to the power 2 into 2 to the power epsilon plus m bar. We have a 2 power 2 here, we have 2 power 4 here, and 2 power 2 epsilon. Two power 4 m bar over 2 power 6 2 power 3 epsilon. Now we combine these and get some constant times n over m bar we have, and we can take m bar out. So this will be m of m bar. Notice that powers of 2 are also cancelled and they all are 2 power 2 at the bottom. So we can leave that here and we have 1 over 2 epsilon plus 1 over 2 power 2 epsilon. So this is less than equal to 1 over 2 power epsilon divided by 1 minus 1 over 2 epsilon. So we have C times n over 4 m bar m of m bar times this is a constant 1 divided by 2 power epsilon over 1 minus 1 over 2 power epsilon. This is just a constant, and the entire cost is T of m bar is less than equal to some constant prime times n over m bar m of m bar, or this is of the order of n by m m m bar. Now, indeed, if the starting matrix were square, then this will cancel out, and we will find that the total cost of LUP decomposition is same as the cost of multiplication of two square matrices. Notice that m bar can be at most 2 times m, hence that is only going to be a constant factor, and we can think of m bar as some constant times m of m. So, we have finally concluded that the computation of inverse of a triangular matrix, computation of multiplication of matrices, and computation of decomposition into triangular matrices, all of them have the same cost. Now, the last thing I would like to point out is that maybe you can just wipe this out, that if you have an arbitrary matrix, a square matrix which is non-singular, then how do we compute the inverse and what would it cost? So, suppose we start with a square matrix T, I can then convert this into L, U, P. Note that all of them will be square now, all of them will be non-singular, and these two will be triangular, lower triangular and upper triangular, for which we have an algorithm to compute the inverse. So, T inverse will be P inverse, U inverse, L inverse. So, that involves computation of 2 inverses. This is trivial, and then the product that will give you, since each step costs order m of the size of the matrix, therefore, this entire process will also cost us order mn time. So, this is where we close the discussion of the matrices.